today, so I expect I'll have a lot of students coming in from that other class for that, but come by at a time when I can return the midterm, that's fine. If you want your cheat sheets back, and actually nobody's asked for it yet, let me know and I'll bring those to class too. And anytime you have questions about the grades, please speak to your TAs. So at this point, let's see about jumping in. And we started talking about sigma and pi, where sigma again corresponded to selection and pi corresponded to projection. And again, sigma selection corresponds to what we've already seen with the where clause, and pi is just like project. As a reminder to everybody, you no longer have to worry about big bad distinct because we're in the set-oriented approach, which means you don't have to worry about multi-sets, assume your duplicates get eliminated all the time. It's not the way things work in relational databases, but it's where relation has started, and we're going to simplify and not deal with a multi-set relational algebra. We looked at how union works. We looked at and we talked about some rules about how union worked, being commutative and associative last time. We also looked at set difference, and again we saw that difference was not commutative. A minus B was not the same as B minus A, and it's not even associative. Same as subtraction. A minus B minus C, whether it's subtraction or set difference, it's not the same thing if you put in parentheses in different places. And then we went on to product, and product is something that we started looking at very early in the term, where we take values that come from R and you jam them together with the values that come from S. So you'll notice that there are 5 attributes in the result, but there are 6 tuples, 3 times 2. We've done that many times. Is it commutative? Not quite, because the order of the attributes changes if you change it to S cross R versus R cross S. Is it associative? Yes. R cross S cross T is the same no matter how you write it. You know, take every attribute in R, jam it together with take every tuple in R, jam it with every tuple with S, and then jam it with every tuple with T. And so, for example, again, if R had 10 tuples in it, and R had 3, and S had, the T had 4, it would be 120 tuples, 10 times 3 times 4 inside the result. And so that's how that works. And the last property we spent a little time talking about toward the end is that just as multiplication distributes over addition, so does product distribute over union, and we talked about why that worked last time. Okay, we looked at a case where there might be a common attribute in both cases, and so one of the ways you can deal with that, we'll come to another, is you say, well, if you take R of ABC and SAE, we don't want to lose anything. We'll have ABC, and instead of DE, we'll have A2 instead of D, because it started off with A, so we'll just have A1 and A2 in terms of the result. And so the original 5 operations that Codd introduced were the 5 that you see on top there: select, project, product, union, and difference. And this is the slide where we stopped last time. There are a whole bunch of other operators that we talked about. And unlike the 5 on top, where if you got rid of any one of them, you wouldn't be able to find a way of getting the one that you got rid of from the others. You can't derive it, and we'll talk a little bit about why that is later. A little hand waving, but we will talk about it. However, these other things, and perhaps you might remember set intersection, but we're going to talk about some actually slightly complicated operators, some of which will come into play later in the term. We'll talk about how those work. All of those can be written using the 5 that were Codd's original 5. And let's see how that works. Theta join is just a fancy way of saying that I'm going to do a product, but there's going to be a selection condition, which might be a join condition on that product. So basically the input to this so-called theta join is going to be 2 relations, R, M attributes in it, S, N attributes in it. And the output is going to be something where you get a subset of the product In other words, all the tuples in the result are going to be things where you jam together, things with A1 through AM, tuples out of R, together with tuples out of S, B1 through BM. But it's not going to be everything. It's going to be only the things that satisfy theta. So the theta join outputs the tuples from the product that satisfy the condition theta. And basically, surprise, that can easily be derived from the 5 things that we talked about before with pi and sigma and product and union and difference minus. Because really it's the same thing as going ahead and take R theta join S. It's the same as taking the product of R and S and then applying the sigma with condition theta associated with it. But this allows us to be able to say we can express joins and other things. We can express what we put inside a where clause and the from clause together. Right? So we can do, the from clause would tell us which things we're joining together, and the stuff that we have inside the theta is what we're doing, joining them together and whatever we're putting in the where clause. And so a lot of what we're talking about here is the basis for why SQL makes sense. Because if the order in the from clause mattered, then SQL might not make sense. And if the order of the things you added together inside the where clause made sense, that made a difference, then where clauses wouldn't make that much sense. So boring examples, we have something where we have students are enrolled in courses and get grades in courses. So in enrollment, we'll have ESID, the student ID, ECID, and grade. Didn't call that E-grade, could have. And then we have course, where there's a course ID, and a course name, and an instructor name. So basically, suppose, maybe somebody can say this. I actually do have it on the slide, so I won't need the whiteboard, because whiteboards are awkward in this room. Give me an example of a theta join to write on the board, where basically I'm saying where the CID in enrollment, ECID, has to equal the CID inside course. Now think about that, it's really easy. It's just a join, simple join clause. Okay, and so basically this thing with an equality predicate, which is usually what you have inside any join, usually it's equality. You basically go ahead and you can write the theta join where theta is enrollment ECID equals course.cid. And so that's all that's being asked for. But you can write any condition. It doesn't have to be something which is a join predicate between enrollment and course. You can write any predicate inside the theta. So you could write something like grade greater than 3.0 or instructor name equals Finkelstein or something like that. And you could do that too. So it doesn't have to be things involving both of the tables involved. And of course, there could be more than 2 tables. Now there's an operation that you may find unnatural, and I suspect that you'll find it particularly unnatural when we get to the really deep theory part of the course near the end. And it's called natural join. That's probably something you've been tempted to have happen, and sometimes it works and sometimes it doesn't semantically. And basically, you have 2 relations, R and S, okay? And here, I'm writing A1 through AK as being the attributes that appear in both R and S. So, for example, you might be tempted, if you have 2 tables that you're joining together and both of them have exchange ID and both of them have symbol, to say, oh, I want to join them together and I want the exchange IDs to equal and I want the symbol to be equal. And for a lot of the tables we've been playing with, that's exactly what you want. And so natural join makes the assumption that when you have attributes that have the same exact name and you're putting together 2 tables and joining them together, that naturally you want the things that happen to have the same attribute name to have equal values between the 2 or more different tables. But we've seen examples in our movie database where you had name, and name could be the name of a studio, and name could be the name of an exec or the name of a star. So just because the attributes in SQL happen to have the same attribute name doesn't mean that they have to be equal when you combine tables together. Maybe Walt Disney has the same name as Disney, but his name is Walt Disney, not Disney Studios. So, I mean, even there, the executive name and the studio name aren't necessarily identical. But natural join, which, you know, often can be something that you want to think about, not always, says we're going to assume when we do the natural join of two tables, we'll treat it as a binary operation here and build on that. When you combine them, what you want to do is always, when you're doing the natural join, the attributes with the same names have to be equal. Okay? So if R and S have common attributes, meaning the same attribute names, not values, this is names, and they have K common attributes, A1 through AK, however many K is. K might be a whole bunch of attributes, K might be no attributes. But basically it says, what you're going to do is you're going to say, we're going to have a relation where we say the common attribute values have to be equal between R and S. And by the way, it would be kind of dumb to keep the common attributes twice. I mean, they're equal. Let's be lazy and just keep them once. Why do the extra work since it's not going to help us? So the idea in a natural join is common attribute names, the values have to be equal when we're taking tuples from R and S and saying, do they match? They have to be equal to match. And we're only going to keep the attributes once rather than twice. Okay? So the meaning of it is, what we're going to do is we're going to take the product of R and S, and then we're going to say, we're going to do a selection. These common attributes, A1 through AK, R.A1 has to equal S.A1. Like R.exchange ID equals S.exchange ID. Okay? And R.A2 has to equal S.A2, like R.symbol has to equal S.symbol, etc. However many common attributes there are. There might be 0, there might be 1, there might be 2, there might be 103. Whatever number there is. It's basically like a selection where you're saying the common attributes names, they have to have matching values in both R and S. And now having done that, what I want to be able to do is take a projection. What's my projection? I want to take the union with no duplicates kept of the attributes of R and the attributes of S. So there are some attributes in R that aren't in S, there are some attributes in S that aren't in R, maybe. And there are some common attributes. So, for example, suppose that R had 10 attributes and S had 8 attributes, and there were 3 attributes in common. How many attributes would there be in the natural join? Let me say that again. R has 10, S has 8, and there are 3 attribute names in common. Something's rattling over there. I don't know if that can be stopped or not. It'd be great if it could be. Maybe closing the window or closing the doors is the easiest. Thank you. So how many think that there would be 18 in the natural join of R and S? How many think that there would be 12? How many think there would be 15? 15 is right. 10 plus 8, but the 3 that you have in common appear once, not twice. So 10 in R, 7 of them not in S. 8 in S, 5 of them not in R. And 3 in common, which only appear once. So it's 7 plus 5 plus 3, or if you will, 10 plus 8 minus 3. Same answer. It's going to be 15. Okay? And of course, this is derived from Codd's original 5 operations because, well, that's the definition of it right there. So again, compute the product, keep only the ones that satisfy matching values for the attributes, and then project on the union where you don't keep attributes names twice because you already know they're equal, so why bother? So that's the natural notion of natural join. So here's a simple example, and unlike the previous case, I'm not calling it ECID, I'm just calling it CID. So suppose in enrollment we have SID, CID, and grade, and we have course where we have course ID, CNAME, and instructor name. In this particular case, there's a total of 6 attributes across the 2 things, but there's only 1 common. So 3 plus 3 minus 1, because I'm only going to keep CID once. The natural join of enrollment and course would have 5 attributes. You would have SID, CID just once, grade, C name, and instructor name. And so that's going to give me, again, a 5 attribute thing that I could choose to call student course grade, which helps give me information about not only the student courses and grades, but also things about the course name and the instructor name. And so that's going to have 5 attributes in it. So that would be okay. Okay? And here's a way I can write the equivalent thing without using natural join, just by using product and sigma. I'm doing sigma only on enrollment CID equals course CID because there's only one common attribute name. And then the pi where I only keep 5 attributes, not, I don't keep all 6 because the CIDs are the same. Here's a tough question. What is the natural join of RNS if they have no common attributes? We'll take hand, name, answer, and I'll give you a hint. The answer is one word. What is going to be the natural join of RNS when there are no common attributes? Go for it.
Null.
How many think it's null? Nope.
Is it Uncle Bear empty set?
What?
Empty set.
It's not null and it's not the empty set. First of all, we don't have any nulls now in relational algebra. It's not the empty set. Yep.
Product.
Yep. You take the product of RNS. You're doing a sigma where anything is true. I mean, you don't have to check for anything as being equal. You're just going to have sigma where the requirement is that all the common attributes are equal. There aren't any common attributes. Well, that's easy. Everything gets into the answer. And then you do the projection on, well, all the attributes in the union, which is everything. So if you go ahead and you do the natural join where there are no common attributes, you get the product. And I bet some of you know what I'm about to ask next. What's a natural join when RNS, all the attributes, RNS have the same number of attributes and all the names are the same. So R has 7 attributes, S has 7 attributes, exactly the same names for the attributes. And I'll tell you again, the answer has one word. Go for it.
Tyler would be the intercept.
How many agree with Tyler that it's the intersection? How many have a different word in mind? Let's be nice. It is the intersection. Because what does it mean? What you're saying is you want to be able to take RNS and you only want things where the attributes match, and all the attributes match, which means the tuples have to be identical. And then you're only going to keep one copy of all the common attributes. So this gives you the same as intercept if all, in the example I gave, all 7 attributes happen to be the same. So that's the intersection. Now we'll have one that, again, corresponds to something that you know about. Let's see if somebody can figure out how this relates to something that you're already very familiar with. It's called the semijoin. It's kind of like a half join. What semijoin, and some of you will think that semijoin doesn't do anything, but it does. Kind of interesting how this works. Basically, what you do is you compute the natural join of R and S. That's what that funny box symbol is, right? X with the lines on the side that we have over here. That's the natural join of R and S. And now what you're going to do, and again, it's not the product, it's a natural join. That's what that funny box thing means on the previous slide. And now what we're going to say is, by the way, we're going to keep the attributes of R. Seems like a lot of work for nothing. How many think that the result is always going to be the same as R? Forewarned is forearmed. It's not the same as R. The interesting question is why? Because you're starting off with R, you're doing the natural join with S, which is basically going to go ahead, and it's only going to keep one copy of common attributes, and it's going to require that there be matching things on the attributes that happen to have the same name. Right? And then it's just going to project only on the attributes of R. And here's the reason why it's not the same as getting back to what you started. I'm teaching 181 and 182 in the spring. So far, nobody has enrolled. Of course, nobody's allowed to enroll yet. Hey, I mean, I get to not have to bother to come in and I still get paid. But the reason people haven't enrolled is nobody's allowed to enroll yet. But it could be that there, after enrollment starts, there are some courses, underwater basket weaving, which nobody enrolls in.
Is that really a course? I wish.
So suppose that you have a situation where some courses have a lot of enrollment and some courses have nobody enrolled in them. What would you get? Remember that we had CID as being the same between course and enrollment. So there is a common attribute between course and enrollment. In fact, we'll go back to this previous slide so that I can remind you. Here's enrollment, 3 attributes, SID, CID, and grade. And course, which is CID, CNAME, and instructor name. So you have courses, and some of the courses have people enrolled in them, and some of the courses don't. Let's take an example. Suppose that Computer Science 180 this quarter had 119 people enrolled in it. And yes, there are still 119 people in the class. As of this morning, anyway. When I go ahead and I look at courses and enrollments and I do the natural join, there is going to be a match because somebody is enrolled in Computer Science 180. There are more than one, but there is somebody. And so when I go ahead and I do the natural join of courses and enrollments, and then I do the projection only on the attributes inside courses, I will get Computer Science 180, get Computer Science 180, Database Systems 1, Shel Finkelstein, etc. That will show up in the answer. Because there is going to be a match of at least one thing inside enrollment. But suppose that there was a course that, we'll call Computer Science 999 that nobody enrolled in. What happens when I try to do the natural join if there are no matching things inside enrollments? The requirement is that I go ahead and I take the product of course and enrollment, and then I do the sigma matching CIDs, just as I did with 180, and then I do the pi where I'm only going to keep attributes once. What's going to happen if nobody is enrolled in Computer Science 999? Well, there's a tuple in course, Computer Science 999, Introduction to Advanced Hieroglyphics, whatever it is. But there will be no matching tuples inside enrollments. And so, as what happens when I do a join of a relation with another relation and there is no match for a tuple, it doesn't survive. It doesn't make it into the answer. So this Computer Science 999 is not going to find any matches. It will not be in the result of the semi-join. So you're going to output the projection on just the attributes of R, but it's not going to be the same thing necessarily as what you started with R. The things that are in R are going to survive are the things that have, well, there are 120 students, 119 registered in Computer Science 180, but we're going set-oriented, which means it either makes it or it doesn't. It only makes it once. So Computer Science 180 will be in the natural join. Computer Science 999 won't be. Can somebody tell me the one word that you should think of that you've already learned that corresponds to this? Hint, it starts with E and ends in S.
That exists.
Yep, that does definitely exist and answer the question correctly. If there exists something inside S that matches R in the common attributes, that R makes it into the answer. It's the same as this. So in particular, find all the courses that have some enrollment. That's the natural join of course and enrollment, with matching CIDs. Find all the faculty members who are advising at least one student, assuming that there's a common attribute, where there's, under student, there's something called, faculty name, which is the name of the student's faculty advisor. Then, you'll have matching things on the faculty name. And so only the faculty members who are advising at least one student will show up in the answer. That's what semi-join does. So it's the same as exists. Find all the faculty members where there exists at least one student where the faculty member is advising the student. Find all the courses that have at least one student enrolled in them. So they closely relate to exists in SQL. Now we're going to have an easy one, intersect. And this is where I may want to just draw quickly on the whiteboard. What does intersect mean? The intersect of Dell desktops and HP desktops is only the tuples that are in both. It's also something you have to do when the things are union compatible. They have the same attributes with the same types. And so the intersect, in this particular case of Dell desktops and HP desktops, is going to be the tuple that's the first tuple in Dell desktops and the last tuple in HP desktops. That's pretty easy to be able to do. That was pretty simple. How would you write it in SQL? Intersect in SQL eliminates duplicates. So you could do that. If you wrote intersect all, it wouldn't eliminate duplicates. But I make the following claim. I made it before, I'll make it again. I have my 5 original COD operators. I don't need to add something new to do intersect. Can anybody tell me how I can do intersect just using sigma, selector, pi, project, x, product, union, U, and minus, which is set difference? Can anybody tell me how to do that? I'm just gonna, I'll raise the screen quickly and then put it down quickly. I'm gonna draw a fast Venn diagram. You got an idea? How would I do it? So, hold on, can't hear you over the screen. Go ahead.
Of like the links for A and B.
Yep.
A union B minus, in parentheses, A minus B minus, close parenthesis, minus, open parenthesis, B minus A.
You're getting there, but it's a lot easier. What you're doing is close to being right. I'm not positive that it is quite right. Okay, yeah, there is a way of doing what you just said. I could do it as A union B minus, parentheses, A minus B, union B minus A. But that would do it, but it's even easier. So let me show you the really easy way of doing it. And it's even shining a light on me, but it's okay. Here are my two relations. Just because I've been using RNS, I will call them RNS. And the intersection is this thing in the middle. I'm going to take R minus S. What do I get? Right? This is R minus S. Everybody agree? And now, I'm going to take everything in R except what's in R minus S. What's in R except what's in R minus S? I wish I had multiple colors chalk, but it's just going to be this crescent. What's in R that isn't in R minus S? The intersection. So I not only can get by with just COD's original 5 operator, I only need one of them used twice. If I take R minus S, that would give me the answer. And a question. Suppose that I wrote S minus R. How many think that would give me intersection also? How many think it wouldn't? Of course it would. It's the same thing. It doesn't mean it's to switch R and S around. That would also give me the intersection. So it's a derived operation in the sense that all I need is COD's original 5, and there you go. And by the way, there you go, right there on the slide. Now we get to the one that everybody detests. Lewis Carroll wrote a number of different things besides Alice in Wonderland and Through the Looking Glass. One saying that is seldom quoted, but worth mentioning, is he explained that the 4 branches of arithmetic are ambition, distraction, amplification, and derision. After you see what division is like, you may agree with the derision part. Division in relational algebra, written with your choice of kind of division sign. This is a hard one. 2 relations R and S where the attributes of S are a subset, a proper subset of the attributes of R. So all the attributes of S appear in R as attributes as well. And attributes of S are non-empty. So it's not an empty set. And the result is going to be a relation whose attributes are all the attributes that appear in R except for the ones that appear in S. Again, remember, attributes of S is a subset of attributes of R. So basically, here's what's going on. We're going to keep the things that are in attributes of R minus S. We're going to keep the values. So here's definition by example, and we'll look at some other cases on the next slide. But suppose that we have R, A, B, C, D, and S of B, D. So the attributes of S are a subset of the attributes of R, proper subsets. And so what we're going to do then is keep the other attributes, the ones that don't appear inside S. So I'm going to have the ACs, value of AC, such that for every single B and D that's in S, the tuples in S are BD tuples, right? For every tuple that's in S, there is a tuple with A, B, C, D, and R. So we're only going to keep the AC, the remaining attributes that exist in R, if for every single tuple that you've got in S, A, B, C, D is inside R. Okay? So an example to help motivate this, and sort of, we've talked about exists. This is kind of like for all. This is like, division is like for all. Find the names of drinkers who like all beers, including Budweiser. Find the names of the drinkers who like every single beer that we have inside the beers info table. So what I want to be able to do is, suppose I have a table likes of drinker beer. I have a table beers info, which gives me the beers and their manufacturers or makers. But I only want to divide not by the beers and makers. The maker isn't part of likes, so I can't divide by beers info. But what I can do is I can take the projection of beers info only on beers. So that way I get a single attribute relation whose only attribute is beer. So I have the list of all the beers that I know about. And basically I'm asking, only give me the names of the drinkers where they like every single beer. Every single one. Okay? So basically, again, another way of writing this mathematically is the quotient or division result, R divided by S, is a relation in which you only keep the attributes that don't appear inside S. You only keep the attributes that don't appear inside S. If for every single tuple, B1 up to BS, no illusion meant, the tuple A1 through AR minus S followed by the B1 through BS appears in R. It may require reordering of the attributes to do this, but it's the same thing question.
So for the first example, if there existed a two